We're going to continue today with more sequencing concepts in SuperCollider, specifically diving a bit deeper into the pattern classes. So to start, I have some code prepared in advance. Some of this is exactly the same preparation code we saw at the beginning of last week's lecture. So I have a chunk of code here which reads buffers, reads audio files into buffers, and it's the same three subfolders: flute samples, glitch samples, and wood samples. So same stuff. And then I have a synth def, which actually I think I need to modify my parentheses. I think this is what I want. Yeah, right. This is a synth def which plays a buffer, optionally filters, applies an envelope. Very simple. This is a synthesis synth def, so it's primarily a sawtooth wave with some random parameters, a resonant low-pass filter, and an envelope. Just in case I want to focus on some pattern concepts with minimal distractions, I have an extremely simple synth def which just is a panned sine wave with an envelope. And then we might also visit some concepts from our lecture on order of execution and groups and buses and things like that. So I have a basic reverb synth as well. And I've made a bus that will allow us to pass signal to the reverb. So I want to start by just playing all of these so we know what we're in for. Okay, basic flute samples, wood samples, etc. The saw and sine synth defs have a gate, so they need to be, communicated with for them to free themselves. Just kind of a chorusy, detuned saw wave cluster. Here's our sine wave. Basic stuff. Let's give ourselves a reverb synth. This is the name of our stereo bus, and we set the reverb to listen to that bus. And we can take advantage of the fact that the default target and add action for a synth is the default group and add to head. So we don't actually have to specify placement of this synth. All we have to do is make sure that the signal is being written to the bus that the reverb effect is listening to. All right. At the end of last week's class, I briefly introduced the concept of a class called event. And event is ultimately a type of collection, in the same way that array is a type of collection. But event is a little bit different. Instead of storing things at ordered numerical indices, event is unordered, and each item in an event is associated with a unique name. So for example, and the event has a syntactical shortcut for creation, which is just to enclose pairs of names and values in parentheses. So we can say ABC is 7, DF 9, DHI 13.5. So E is an event, its keys are A, B, C, D, E, F, G, H, I. You can just notice from the way it prints that it does not consider these to exist in any particular order. They're just free-floating names, and each name has a value associated with it and can be retrieved by simply asking the array what is stored at this name. And these names are usually called keys. So an event consists of key-value pairs. So from this perspective, it's a very, very simple class. It's basically a storage mechanism, and it has the advantage over arrays of being able to give the data stored in there meaningful names instead of saying the item at index 0, index 1, index 2, etc. But the event class is used for much more than this, and in fact, there's a complex structure that's part of the SuperCollider language that allows us to use events to express the creation of and manipulation of sounds. And I believe there's a discussion about this. If we go down to, if we search for synth-def in the event file, there's a section titled Events and synth-defs, and it gives you sort of a brief discussion and example of what is, how events are used in conjunction with synth-defs. So I'll give you a brief demonstration of my own. I think we started with this last time. If we have an empty event and we say .play, a sound is created. And so there are a bunch of keys that an event expects, and keys which have predefined meanings in this context. One of which is freak. Another one is amp. So the question then is, where does the recipe for this sound come from? It's in fact in the source code for event. We can click on or highlight the name of a class and press Command I, and then enter to bring up the code which defines its behavior. And if we do a find for synth-def, we see that there's a method called makeDefaultSynthDef, and here it is. So you can study it at your leisure, but basically this is a synth-def that's automatically added to our synth-def library for us, so that when you play an empty event, there is some basic information there. It has a default synth-def that it can refer to, and there's basically all of the information has default values there. So we actually don't need to specify anything, but the design of event and its use for playing synths allows us to easily sort of specify our own synth-def, our own values, our own this, our own that. It's very, very flexible. Basically, this is a sawtooth wave which has been filtered and has a linear envelope. There's really nothing else. It's a pretty basic synth-def. So let's recreate this synth call using events. So instead of saying synth or synth.new, we say instrument samp buff the buffer we want to play, and amp 0.7. So the same result, just different way of executing it. And if we stop here, it seems, okay, what is the difference? What's the advantage here of using events versus just creating a synth directly? And there are a few. For example, if we do our saw synth like this, normally we create the synth, and then we have to set its gate to 0 to fade it out. if we do it this way, it stops automatically. And that is because among the many keys that are predefined in the event substructure, one of those keys is a key named sustain, which I think has a default value of something like 0.8. And it refers to a number of beats which should allow, it specifies the number of beats to elapse between the creation of the synth and when the corresponding gate 0 message is sent. So if we set this to something like 3, at approximately 3 seconds, and then the gate message, basically this, telling the synth that this event created, set your gate to 0, happens automatically. If we set this to something very small, the synth will be created, and almost immediately the gate 0 message will be sent, and the release phase of the envelope will be triggered. So essentially, to keep things relatively simple for now, instrument is a key which specifies the name of the synth to be used. And once you've done that, you are free to specify additional arguments which have been declared in that synth. So amp, freak, etc. And then there are also some keys, like sustain, which are inherent to the event structure. There is no sustain key defined in this sawtooth synth. Nothing called sustain, but it has meaning. So we're basically adding another layer here where we say, let's make an event. We specify some event keys. That event, when we play the event, it gets translated into an action, and the default action is to make a synth. And then it uses the data in that event to populate the necessary data to make a synth. So we're basically creating a synth by translating it through the playing of an event. There's some more to talk about here, but I think the more we discuss the nuances of event, the further we get from practical applications. And I think it's generally a little bit better to just show the practical usage of event. So the reason we're introducing event, because there is a pattern by the name of Pbind, which in some ways is a lot like the patterns we saw last week, like pseek, pwhite, prand, etc. But instead of specifying a sequence of values, usually numbers, Pbind specifies a sequence of events. It's a way of automating the process of generating and playing these event structures. And so we simply need to provide Pbind with several key value pairs. For example, instrument, let's do sine. And we can say amp 0.1, freak 400. And then we'll say seek equals p dot as stream, like we did last class. And you remember that patterns specify the creation of a sequence of data, but it's not the execution of that sequence. Instead, to actually retrieve and use values from a pattern, it has to be converted to a stream. So that's what we're doing here. And now we can talk to the stream and say dot next. And we are accustomed to being able to just call this as it is, but for event patterns like Pbind, we actually need to provide an empty event to the next call. This looks a little bit weird, I know, the double set of parentheses, but basically we need to provide an empty event for Pbind to populate. Basically, we pass it an empty event, it will fill it with the values here, and then give us the result. I think. Yeah, there we go. So let's do that again. So we make our pattern, we create a stream from that pattern, and then we say give me the next event. And it is an event whose instrument is sine, its freq is 400, and its amp is 0.1. So we could say dot play. All right, and this is a pretty boring sequence. There's really not too much going on here. The real strength of Pbind here is that we do not have to provide fixed values for any particular key. We can provide a value pattern. For example, we'll say pseq 200, 300, 400. So we're specifying a value pattern which outputs the sequence 200, 300, 400 forever and feeds those values into freq every time a new event is requested. So let's actually, I think if we post the event first and then play it, we'll get to see. And you know what? I'm gonna do a little trick I like to do here and put a empty symbol at the end here, and this effectively mutes the fact that SuperCollider is verbose and always posts the thing you evaluate. So now it'll just post the event and then play it without posting any additional information. Right, so the actual the printing is silent, but we are explicitly requesting the event. And so on and so forth. We can provide another pseq here. So let's say 0.5, 0.4 inf. So a quiet 200, allowed 300. So it really doesn't matter. You know, these value patterns don't have to be the same size array. They can, in this case, they in a sense they drift out of phase. We have a 2 against 3 pattern here. Pbind doesn't care. Every time we ask it to make a new, to play a new event, or, you know, to give us the next event, and again, we're not talking to Pbind. We're talking to the stream. We say give us the next event, and it just retrieves the next value from all of its patterns or static values, and populates the event. So I suppose that's pretty useful. Let's do another example, but this time we'll use our buffer playing synth-def. We'll say prand, and we'll select B at flute at 0, B at glitch at 0, and B at wood at 0. And we'll say pxbrand. And I think there's no freq key in this synth-def, so if we kept this here, it would be sort of harmless, wouldn't really do anything. But we do have an argument called rate, and we'll say pwhite -12, 0 .midi ratio. It's a little quiet. I'm going to change this to be louder. And I want to emphasize that extra stuff here, like a key called fmerg, doesn't, you know, it will get passed into the event, but this particular key has no meaning. It's basically an extraneous piece of data in the event, which does not have any inherent meaning to event or to the synth-def. So it's just simply present, but has no influence on the sound. So it's sort of the user's responsibility to use keys which are meaningful and do the things you want to do. Here's another thing we can do. If we say out bus, then we're specifying the creation of a synth, and the output argument in the synth-def is the reverb destination. And if we go back to our synth-def, We have the start position, the attack, the sustain, and the release of the envelope. We could filter it. So we have lots of additional options, and very careful, precise specification of value patterns for these arguments can give us very complex and sophisticated and interesting sequences. All right. So next, I want to address the fact that manually playing these events is not what we'd like to do is say go and then step back and let SuperCollider handle the rest. So instead of saying as stream and next and actually retrieving the values manually, we can simply say play. So we have a pattern, and then we'd like to play it and store the result of the play method in seek. And so it's doing its thing. We can say seek.stop. Remember, we're talking to the tangible execution of this pattern, which is technically it's an object called an event stream player. It's a relative of stream. I think it's a subclass of stream, and it behaves much in the same way. But instead of something which relies on the user to manually call next on it, it actually handles the timed scheduling of the playing of every synth that comes out of this Pbind. We can resume, and it picks up from where it left off. It sort of knows where it was. This is not a good example. Like, for example, if we were playing a scale, let's actually do that. Let's change this so that it's always the flute sample, and this will be seek. Remember, this is a shortcut for creating the array between these integers. Okay. The question then is, what determines the durational values, right? Why is it this fast? Why is it this slow? Where does it all come from? Well, there's another innate key in the context of playing a Pbind, which is dur. And dur is a value in beats to wait between the onset of one event and the onset of the next event. The default value in for the event is 1, and this means 1 beat. And when we play a Pbind, it gets scheduled on a clock, and the default clock has a tempo of 60 beats per minute. So saying dur 1 is, under default circumstances, it could mean 1 second, it could mean 1 beat. They are equivalent. So I just cannot stress enough how much default structure there is. There's so many things that have been sort of taken care of and are ready for you to use, and if you don't specify a complete set of information, you will never get a situation where it's like, hey, you didn't specify this. It's going to fill in the blanks with some data, and it's up to you to override that data if you want it to be different. So if we say 0.5, these will be twice as fast, or 10 times as fast. That's weird. Oh, you know why? Because I hit Command period, and poof goes my reverb. So let's make that here. Or you know what? Let's just, you can imagine, let's just send it straight to. Right. Alrighty. On the topic of dur, it's not always convenient to think about metric values as some mathematical division of 60 beats per minute. If you want to do something at 108 beats per minute or 132 beats per minute, it's possible to do that, and you do not have to do a bunch of wacky math with this value. To do so, all you have to do is simply make your own clock. and set that clock to be running at some desired tempo. And then you can specify your dir values as some simple division of beats on that clock. So for this, we're going to introduce tempo clock. A tempo clock is the primary clock that we use for playing and scheduling events through patterns. And it takes a few input arguments, but really the only crucial one is the first one, which is the tempo expressed in beats per second. So if you put a value of 60, this is actually 60 beats per second, which is wrong. It's probably not what you want. It's incredibly fast. So I usually specify some tempo in beats per minute and then divide by 60. And this gives you a tempo clock running at 108 beats per minute. Nothing fancy happens, but this clock comes into existence and in the background starts counting beats. And we can sort of say, hey, where are you? It says, oh, I'm on beat 18.74, blah, 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 blah. So it's a very precise clock, and it's just going to count beats at 108 beats per minute. All right, so how does that help us? Well, we can say, give me, if we think about, like, this is one beat at 108 beats per minute, you can think of it as a quarter note, if that helps. And we just have to be sure to play this pattern on this clock. And I think the arguments it accepts here are, the clock is the first one. So this will, let's do t.tempo. We can see it's still 108 over 60, but we can update the say 132, 164, 80. Right. If you press Command period, the tempo clocks by default will not survive. So if you hit Command period and try to play this again, it says clock is not running, because Command period destroys tempo clocks by default. But we can make a tempo clock survive Command period by setting its permanent attribute to be true. So we've remade this clock, and we can play this pattern again, stop it. If we hit Command period here, still works. The tempo clock is still running. It's still counting beats in the background. Right. And I think we just say t.stop to destroy that clock. So now it's gone. We might come back to clocks at some point, but I'd like to dive a little bit deeper into the structure of events. So we're going to change a few things here. And let's say attack. A short attack. I have to remind myself what how I did this. So I have attack, decay. Oh yeah, it's an attack, decay, sustain, release envelope, I believe. Right. It's got 4 points, and it will sustain at the sustain level. So. Okay, so the decay longer, but still pretty short, and the release like this. And so we can put sustain in here, and this will be the number of beats. It makes the note, and then some number of beats later, it sends a gate 0 message. So we'll have this be 0.2 seconds. I'm saying seconds because we're playing this on the default tempo clock. Seconds equals beats. So let's see what this sounds like. Make this a little quieter. Too quiet. If we let this play, this particular event stream player, it will go on forever. And that is because every one of the values at every one of the keys is either an infinite length pattern or a single value. And in this context, a single value is interpreted as an infinite length pattern which only produces that value. It's basically the equivalent of this. Same thing. The length of the shortest value pattern determines the length of the event stream. So in this case, we will get exactly 6 events. And that's it. As soon as one of the value streams returns nil, that's the event stream player's cue to say, oh, we must be done. That's the end. So all right. I'd now like to take a closer look at amp and freak. These are a little bit special in the context of events. And in fact, I want to take a peek under the hood a little bit, and I'm going to open my notes here and grab some code that I've prepared in advance. And there's a couple of expressions which allow us to actually look at the underlying structure of event. And I want to look at the default events amp key. So basically, there's a default event, and it has a bunch of default parameters, basically a bunch of keys with default values. And the default key for amp is actually a function, which takes the value at another key, dB, and converts it to amplitude. So okay, fine, let's look at dB. And at dB, there's a value of minus 20 decibels. So basically, if we don't specify any amplitude information, the internal dB key has a value of minus 20, which is converted to amplitude and plugged into the amp key. And then amp is at the top, basically the top level, and that's the value that actually gets passed into a synth-def. And if there happens to be an argument named amp in the synth-def, then that value gets plugged in to the synth that is created from that call. So this means we can alternatively specify a value in decibels. So something like, it's important to be careful here because these would be pretty terrible amplitude values. They'd be 10 to 30 times greater than nominal amplitude, and they'd also flip the signal upside down because they're negative. But if we provide these for dB, then these values, we can actually do the calculation over here, get converted into the corresponding amplitude values, whatever they happen to be. So we can just do this. Oh yeah, and let's make this infinite again, and let's make this a little more interesting. So there's amplitude variation, but we have the flexibility of specifying it in decibels if we like. If we specify it in amp, like this, also fine. And what happens in this case is by specifying amp, these values actually, for each event, overwrite this function. They say, okay, forget about that function. That's gone. Just use this value instead. And this is really, really nice. I mean, it's just a nice, clever design which allows us to specify dB or amp. Now, if we had named that argument in our synth-def something different, like instead of amp, we named this vol, for volume. This is fine, of course, and the default value is 0.3. But by choosing to name this argument vol instead of amp, we're voluntarily giving up the ability to specify amplitude in amplitude or decibels using these keys. And this is kind of a subtle thing here. So now if we say vol, this is fine. This will work just fine. You can hear we have amplitude variation. But if we say dB, p white, minus 30, minus 10, inf, they're all the same level. All the same level. And that is because internally, decibels are being converted to amplitude and being supplied to the amp key, but that name has no meaning in the synth def anymore. And instead, what happens is when we make the synth, we're just using the default vol value, which is 0.3. Now, we could, of course, do this. This is fine, too. This will work just fine. This is basically, we're making this functionality for ourselves. We're saying, okay, fine, I'll do the calculation. So that's fine as well. But I think generally it's a good idea to use the specific name amp in your synth defs, because then it's just a little bit more of an elegant way of expressing things. You can pick amp, you can pick dB, etc. So I'm going to go ahead and change this back. And so now we do something like this, and we're back where we started from. So that's the amp dB hierarchy, so to speak. And I want to take this moment to point out that in the event help file, down at the bottom, there's useful keys for notes. So when we're using events to make synths or make note events, as they're called, it says amp event keys. So for example, amp is expressed, as we know, as a dB key converted to amplitude, and this is the default value for dB. And I'd like to look at pitch, actually, because pitch is using a similar hierarchy, but it's more complex. Basically, we start at a key called degree, which has a value of 0. And degree, actually, a good way to look at it is, it's so small, let's make this bigger here. This diagram, and actually I'm going to make this as big as I can here. The lowest tier is degree, which also, which basically, it's like index. It's an integer index into an array of scale degrees. Or actually, degree is a scale degree, and scale is sort of semitones, right? 0, 2, 4, 5, 7, 9, 11 is the major scale. And then we can also do a modal transposition, basically just shifting along the scale. The next level, basically these data are translated into a key called note, which is more akin to 0, 1, 2, 3, 4, 5 are semitones. And then we can also do various manipulations at this tier, for example, changing the number of steps per octave, changing the octave ratio to be something other than 2 to 1, various exotic temperament things. This gets translated into a MIDI note key, and this is 60 is middle C, 72 is an octave above. From there, we can do a chromatic transposition, specify a harmonic number, basically multiplying the corresponding frequency, and an additive detune, and this all gets translated into freak. To be perfectly honest, I find myself working just at freak if I just want to specify raw frequency values. Sometimes I'll work at MIDI note numbers. And rarely I might find myself working with scale degrees. So I'd like to show these tiers to the extent that I understand them using this Pbind here. Right, so freak is pretty straightforward. It's just a value in frequency. And again, it's in our best interests to name the argument that represents the cycles per second of some oscillator FREQ. Use that name, because by doing so, we give ourselves access to degree, note, and MIDI note, because they all bubble up to a key named freak. If we name it hertz or tone or whatever, it'll still work, but we'll have to do a lot more work if we want to be able to specify pitch information in a way other than the raw frequency value. So if we say degree, and let's make this a little slower. And if we do something like this, we're going to get the first 5 scale degrees of the default scale, which is a major scale. And we can do something like, this makes it very nice. It's a nice way to create textures and patterns and arpeggiations in a particular scale, and just give it sort of free reign within this. You pick the notes which are correct notes, so there's no wrong notes, so to speak. So we can say like go down or up, and there are 7 scale degrees, right? C, D, E, F, G, A, B, right? So we can go from C, so 0, 1, 2, 3, 4, 5, 6, 7 is the next C. Every multiple of 7 in this case is a C. So we could just do something like this. Let's make things a little more interesting. PX range. No, what am I doing? PX brand. And we'll do this. Or maybe if we choose to specify the pitch as degrees, then we can say, let's specify a scale. And let's do the minor pentatonic scale. This. So it's an array of scale degrees. And let's shrink this a little bit. We can bring this range up. And then M transpose. It's basically an offset for degree. So if we say M transpose 2, it's gone up. Basically, it shifts the entire thing up by 2 scale degrees. So it's the equivalent, I think, of just saying this. Yeah, but we have the option of specifying it as a separate key if we want. So that's degree, scale, and M transpose. And then next, if we, obviously it doesn't make sense to mix and match. Like you wouldn't specify degree and note and MIDI note and freak, right? Those are likely to be conflicting, and what's going to happen is whichever one is higher up, or in the case of this diagram, more towards the right, is going to ignore the previous ones, right? Whenever we specify like MIDI note, we're basically saying whatever function you're using to calculate MIDI note, forget about it. Just use this value. So let's look at note. So if we just say pseq 0.12, so 0 is still middle C, I think, but just these note numbers represent semitones. So let's just see what happens if we say octave ratio 2.2. So we basically stretched the octave so that it's larger than usual, and so we get some interesting microtones. What else can we do? Is it? Yeah. Let's change this back to 2. Octave. I think if we just say 1. Oh, okay, right. Yeah, so this is like a 5 is the octave on the piano, which has middle C at the beginning, and we can shift it around if we want. So if we say this, and then G transpose. So this is I think the G stands for gamut, G-A-M-U-T, gamut transposition. Doesn't have to be an integer. So you have a lot of flexibility here as well. MIDI note, pretty straightforward. Let's do 40, 47, 57. 62. MIDI note numbers, C transpose. It's again just a chromatic shift for a value of 1. And harmonic. This is the harmonic number. So if we have 1, so it's basically going up the harmonic series at this point. So if we just make this a permanent 29, and then set this to go 1 dot dot 8, then we'll get the first 8 harmonics of a MIDI note 29. I forgot something, and it's this parenthesis over here. Yeah, and I think we can say detune, and this is a value in hertz. So detuning each one by a specific value in hertz. And yeah, and I just can't really stress enough that this is still a very simple pattern because so many of the values are fixed. The really exotic stuff happens if you very carefully, very like weighted randomness with very specific choices, doing something more exciting with the durational values. Let me before we go, I'd like to try to make one semi-interesting pattern, and I think what I'm going to do is use pgeom to create these sort of exponentially increasing and decreasing parameters. So we'll start at a value of 0.02, and we want to be careful to increase this value by a little bit. And we'll say inf. This is kind of harmless, I think. It just means the duration values are going to get larger and larger and larger, and eventually it'll be so sparse. What we don't want to do is something like this. This would be bad because the duration values will get shorter and shorter and shorter, and eventually be so small that we're going to be asking for too much in too small an amount of time. So let's say P series for dB will start at -6 and decrease by a fifth of a decibel each time. I think we have a rate argument. We'll say pgeom start at a rate value of 1 and drop that by a tiny amount. We could also think in terms of semitones, like go down by 1/10 of a semitone forever. I'm tempted to stop here and just see what this sounds like. Let's make this a little bit longer. Oh, I need to say what buffer I want to play. We can do, and then I'll just make a few more. Let's say times just some random value. 0.8, 1.25. Is that working? Let's stop this for a second. Is that actually bouncing back and forth? I don't think it is. I might have done something wrong here. One. Pan. I don't know. I don't, something simple I'm overlooking, but it could be in the synth. It could be at the analog mixer behind me. I can't tell at the moment, but I thought this would bounce back. It should, It's something is amiss. Is there anything else fun we can do? I guess we can make the pitch go let's say go in either direction every time we make a new one of these. No, that's the decibels. What am I doing? I messed with the wrong pattern. Let's see. So we're going to do Prand. We're either going to pick that one or this one. And we're going to make this random choice once, but each one of these internal ones is infinite. Come on, go down. There we go. You can imagine sending this to Reverb would sound a little nicer too. So I'm also being kind of messy here because each time I run this code, it's overwriting the previous event stream player with the new one. So what I should be doing is, you know, well, yeah, I could make an array, or I could do something like this. No, it's always the same. I think it's because, why is that? I guess it makes this choice when the pattern is created, which I thought, is that? No, it doesn't. But it definitely makes this choice. This is a permanent choice here. So really what I should be doing is specifying a pattern here that picks a random value and then repeats that indefinitely, instead of basically burning this language side value into the Pbind. Right? So you always want to think in terms of patterns when you're inside of a Pbind. So I'm going to end it here for today. I think there's actually even more sequencing and pattern stuff to talk about, so we'll probably tidy that up next week. But I will assign a homework assignment this week, and the midterm is due at 3 tomorrow. Good. All right. Stick around if you have questions, and I'll see you then.